Welcome to the preparation videos of the course Mathematical Foundations in Software Engineering. This is the sixth video in the series on statistics and probability, and in this video we will talk about regression. Very often in science or engineering we want to build a statistical model that we can use to predict what will happen. In another video we talked about the relationship between lines of code and faults. What we actually did in that example was to use linear regression to build a model that we then could use to predict the lines of code in a certain piece of software. We will now use that example in this video. We will start by introducing you to what we mean by a model. Then we will plot the data to get a feeling for it. After that, we will check for suspicious outliers and check for normality and correlation. When we have done that, we will, by hand, build our linear model. Then we'll check if it is statistically significant and we'll conclude by looking at ways to validate our model. The aim of linear regression is to model a continuous variable y as a mathematical foundation of one or more x variables. The idea is that we will be able to forecast the y when only the x is known. This mathematical equation can be generalized as follows: y equals alpha plus beta times x plus epsilon. The epsilon is the error term, and since a model is almost never perfect, we need to have a part of y the regression model is unable to explain, that is, epsilon. Alpha is called the intercept, while beta is called the slope. So, where we start on the y-axis and the degree of the slope, which can be positive or negative. In this case, it's rising, so it is positive. Let us now start with our example. Do you remember this table? Probably you do. Let's start by plotting it in different ways. So I've taken exactly the data we had in the table. I didn't download any data now, and I stored the data in a variable in RStudio. Then I called three different functions: scatter.smooth, boxplot, and plot. And in the latter function, I chose to plot the density. So what do we see in these plots? Let's go from left to right. The scatter plot suggests that there is a linearly increasing relationship between lines of code and faults. We like that, since it is additive and linear. So, what does the box plots tell us? Well, there are two data points that could be considered outliers. For log, it's the value 33,900. That seems to be very high. For faults, it's the value 62, which also seems to be very high compared to the other values. I calculated this by looking for data points that are outside 1.5 times the interquartile range, or 1.5 times IQR. The IQR is, in its turn, the distance between the 25th percentile and the 75th percentile values. Now we have a choice to make. Should we remove them before we continue, or should we keep them? Let us keep them. We'll see how good our model will be, and if the model is not very good, then we could go back and remove them. However, after we have checked why they exist. In short, we better have an explanation before we remove any data. The last plot to look at is the kernel density plot. Well, I don't know about you, but the data does not seem to be normally distributed. And you do remember how we checked for correlation using RStudio, right? It showed a fairly strong positive correlation. This is good. That is, that it is fairly strong. If it's positive or negative doesn't really matter. So, okay, now we have a feeling for the data. Let us now introduce some of the basic concepts we need to have when conducting a linear regression by hand. In order for us to build a statistical model of the data, in this case a linear model, we need to find the least squares estimators of beta and alpha for our data set. What we do is to first find the least squares estimator for beta, the middle equation, which we then use to solve alpha, the bottom equation. The hats the letters have denote that they are estimates of a value. So beta hat is an estimator for the true beta. The easiest way to deal with an equation which has a lot of summation is to do it step by step. In the first and second column, you see our data points. In the third and fourth column, we have the results of taking the data point minus the mean, and in the fifth and sixth column, we have the square of that difference for each data point. In the final column, we multiply the differences for xi and yi minus their means. In the last two rows, we have sums for some columns, and the means for our two variables x and y. The values we are interested in for calculating the beta are the ones circled in red. Let us now calculate the beta estimator. Not very hard, right? And remember, if we have the beta estimator, we can now calculate alpha using the values we've calculated before, now circled red.